In our last video, we looked at a couple of different ways to examine the kinetic energy of particles in a gas. For this section, we're going to look at some common relationships and then also talk about another way that we can look at kinetic energy or total energy of a gas. So we had these two equations for kinetic energy, and this one was for the average kinetic energy of particles in some gas at a temperature T, and that's T is in Kelvin. And then this is just the general equation for kinetic energy, K equals 1/2 mv squared. Well, if we want the kinetic energy of a single atom or a single molecule of a gas, when we're talking about monatomic ideal gases, really we should be talking about atoms, not molecules, then we can write this as K equals 1/2, and then for the mass, I'm going to put in the molar mass divided by Avogadro's number, that's 6.02 times 10 to the 23rd. So the molar mass, that's the mass of 1 mole of a substance. And then Avogadro's number here, that's the number of particles in 1 mole. And that's going to be equal to v squared. So now I'll set these two equations equal to each other. And we've got 3/2 times Kb times T, the absolute temperature, is equal to 1/2 times m over n naught, molar mass over Avogadro's number, times v squared. And so we can multiply both sides by 2 to cancel this, and then we got, let's isolate v here. We can solve for the velocity or average velocity of a particle here. So we'll multiply both sides by n naught, so 3 kb times n naught, then divide both sides by the molar mass, capital M, is equal to v squared. And so if I just rearrange this a little bit, we've got v is going to be equal to the square root of 3 kb times n naught divided by m. Alright, now this equation works just fine, and that would work for us. Oops, I forgot a t here. T, there we go. So that equation would work just fine for us, though it's a little bit cumbersome to write this out. We should also specify this is the average velocity, or the root mean square velocity. If we square all the velocities of the particles and then average that together and then take the square root, that's what root mean square velocity means for all the different particles here. It's a little bit cumbersome to write this out because we've got the 3 and then kb, that's a value of 1.38 times 10 to the negative 23rd joules per Kelvin. And then n naught, the Avogadro's number, is 6.02 times 10 to the positive 23rd. And that's moles to the negative 1 power, or inverse of moles, times T divided by the molar mass. So I've got this number that's times 10 to the 23rd and times negative 23rd and times 10 to the 23rd over here. So it seems a little annoying to be writing that out this way the whole time. And it turns out that Kb and n naught are fairly frequently multiplied together in equations that we're going to work with. So it's useful just to establish a quantity R, which is called the ideal gas constant, which is equal just to Boltzmann's constant times Avogadro's number. And so this value R, it turns out when we do the 1.38 and then 10 to the negative 23rd, and the 6.02, 10 to the positive 23rd, we get a number that's really easy to work with of 8.31. No times 10 to any power here, or just times 10 to the 0 power, I guess. And then the units on that, we've got joules divided by Kelvin, and then the moles is in the denominator as well, so it's joules per mole Kelvin. moles times kelvins in the bottom of the fraction there. So this is the value for R that we're going to use. So I could take this earlier equation and rewrite that as V RMS is equal to the square root of 3 RT over M. Okay, so that's handy. That'd be a nice way to write this out. Another thing that we're asked to do in this this learning target, in addition just to understanding that, hey, it's a pain to write these out every time multiplied together. Let's just use the product of those as a new constant. It's useful to be able to figure out what the energy of a mole of gas would be as a function of its time. So if we use what we know already, the energy, we're looking at the K, the kinetic energy of 1 mole, is just going to be equal to 1 mole, or and not Avogadro's number, that many particles added together, or times K average. So this is going to be the same as N naught, let me change my phrasing a little bit here. So that'd be N naught times 1/2 mv squared. So we're just multiplying the N naught by the equation for 1/2 m, or for kinetic energy there. And I'm going to use this notation, you'll see why in just a minute. K is going to be equal to N naught times 1/2 times our mass, which is going to be that molar mass divided by N naught again. Okay, so we're going to see that that'll cancel out. That'll be nice. And then our VRMS, or our velocity, is going to be the VRMS that we calculated here, the average velocity. We square that, so we can just write that as 3RT over molar mass. Okay, and our molar mass then is going to cancel as well. So our kinetic energy of 1 mole then, the total kinetic energy, is just going to be whatever's left here. We've got 3/2 times R, the ideal gas constant, times the absolute temperature. It's the total energy for 1 mole of this gas. Now really that's just total kinetic energy, but if we assume what we did in the kinetic theory of matter, that basically there's no interactions between particles in a gas, and here it says we're talking about a gas, except when they collide, then all of the energy in this gas is going to be kinetic energy. So this is just the total energy that's stored in this gas, and we can see all it depends on is the temperature when we've got a set value for the gas. So this is where we get that relationship of that we used earlier. We kind of worked in a circular manner here, but we could rewrite this using KB as well and get that very similar equation to what we worked with earlier. So this is for 1 mole. The other one was for 1 particle. That's the main difference that we're seeing here.